Okay, now let's do a quick example. And a quick example that it is taken from again Flat's book 10.4. It says the mid-range voltage gain of a certain amplifier is 100. So it means that the mid-range gain is what is the maximum or unaffected gain of the amplifier. So the unaffected gain occurs. Okay, this is the mid-range gain, and this is the mid-range frequency as well. So the gain over this frequency range would be constant, would be unaffected, and it is given by 100. Okay, so the gain somewhere over here we can write this is equal to 100. Now this is 100. The input RC circuit has a low critical frequency of 1 kilohertz. So the input RC circuit is given by this input RC circuit. So for simplicity we can assume this part, we can ignore this part, neglect this part. Okay, so for the inputs, okay, RC circuit, the critical frequency occurs at 1 kilohertz. So it means that the critical frequency FC, okay, I can write this as FC. Let's suppose this is 1 kilohertz. Okay, so 1000 hertz, I can say 1000 hertz, 1000 hertz. Okay, sorry, I can rewrite this basically. So this is basically, I can write this FC is equal to 1000 hertz, 1000 hertz, right? Okay, and determine the actual voltage gain at F, at the critical frequency, then when the frequency is reduced. Okay, and then when a frequency is reduced further. So it means that this is FC, this one is FC. Okay, and let's calculate this 100 is what. If you see this 100 hertz, this one is this, if I call this is F2, okay, is equal to 100 hertz. Okay, and remember if I calculate the ratio, so it will be this is the first, okay, 0.1 FC, okay, the first decade frequency, and into FC. So if I this is 1 by 10, okay, and critical frequency was 1000. So it means that this is equal to 100. So it means that this is 0.1 FC, this F2. So this one is this over here, this is F2. And similarly you can prove this 10 as a further reduction by 0.001 of the cutoff frequency. So basically this would be actually is F3. So it in the question it is required that what should be the voltage reduction in the voltage gain at this frequency, at this frequency, and at this frequency. So we know that the voltage gain reduction, okay, at FC is minus 3 dBs, okay, by mathematically we proved that, and this is minus 20 dBs over here. For this is minus 20 dBs, okay, this is 10 by, and over here it is further minus 20, so it becomes 40 dBs. See over here, 40 dBs. Okay, now so if this is, it was 100, okay, so 100 and minus 3 dBs. Okay, now remember minus 3 dBs was 0.707, the voltage ratio was 0.707. So minus 3 dB correspond to 0.707 times 100, it will be equal to how much? 70.7. So it means that over here the voltage would be drops to 70, okay, volts. What about this one? Okay, this one, if you see this corresponds to minus 20 dBs. So minus 20 dBs, okay, what should be this ratio? Okay, minus 20 dBs, so that when you multiply with 100 you would get a further decrease in the voltage. So minus 20 dBs, last time we proved that it corresponds to 0.1, or you can do it with the calculator over here. with the calculator. The same thing over here last time we find in the previous slide, so no need to do it again. So it will become what? It will become 10. Okay, so it means that from 100 now the voltage is 10 volts. And then the same thing we can repeat, and this is 40 minus 40 dBs correspond to minus point sorry 0.01 times 100. Okay, 100 is the normal initial gain, so it would give us what? 1. So it means that from 100, okay, the gain drops to 70, and then the gain drops to 10, and then there is a gain reduction to 1. Okay, so from 100, okay, the voltage gain, okay, was decreased to, okay, we can say was to 1 volts, to just one, not 1 volt, to just 1. So it means 1 volts in case you're talking about voltage. So this is because when the reduction when reduction in frequencies occurs, so it affect the voltage gain, and the voltage gain reduces by AV by a certain factor to 1. Now in the next slide we say, okay, next slide it talks about the phase shift. Now remember the phase shift, very simple, for any RC circuit, it will results in a phase shift, either a leading phase shift or a lagging phase shift. Now over here, this is the circuit. Over here it corresponds to a high pass RC circuit. So for our high pass RC circuit, the phase shift is given by this formula, XC1 divided by Rn. Now let's talk about calculate some values of the phases shifts at different frequencies. So when frequencies, remember, if I plot that plot, okay, it was like this thing, is like this thing, this was reduction in, this was frequency, and this axis was voltage gain, okay, V. So when for a mid-range frequencies, okay, from here to here, okay, there was no change in the values of voltage gain, no reduction in the voltage gain, and this was the mid-range frequency, and the voltage gain was the mid-range gain, right? Okay, so this occurred at a frequencies which was very high, okay, high from the critical frequencies. Okay, so XC can be effectively assumed to be 0. So when XC is 0, if you put the value of 0 over here, take the tan inverse, okay, so it comes to be 0. So it means the phase shift for this frequencies, for increasing frequency, is 0. And this was FC, okay, this point was FC. Now when I decrease the frequencies further down from FC, what would happen? That XC would be non-zero, and okay, and we can calculate the phase shift. But at this critical frequency, okay, remember the condition for critical frequency occurs when XC is equal to this Rn, sorry. So when XC, put the value of XC Rn, take the 10, so this is 45, right? Okay, and then if at a decade below the critical frequency, okay, a decade at 0.1 FC, okay, when this was the value of 0.1 FC, okay, the condition we proved that this XC1 becomes equal to 10 Rn, so the reactance becomes very high. So so if you put the value of XC, it gives to be 84.3. So it means that okay, thank you.